All right, so for ACT prep, the first thing we're going to do, the first lesson we're going to look at is number types. So I want to discuss number types, and if you were in my class ever, I always call it classification of the real number system. So we talked about things like irrational numbers, rational numbers, integers, whole numbers, natural numbers, things like that. Those are number types. But before we get into the number types or the real number system, you need to be familiar with perfect squares and their square roots. So I'm going to list perfect squares. Perfect squares are the product of two numbers being multiplied by itself, well, by a number being multiplied by itself. Like the product of 1 times 1 is 1, so therefore 1 is a perfect square. The product of 2 times 2 is 4, so 4 is a perfect square. The product of 3 times 3 is 9, so 9 is a perfect square. The product of 4 times 4 is 16, so 16 is a perfect square. So you should get what I'm doing once I start listing these perfect squares. The next perfect square is 25, because 5 times 5 is 25, 6 times 6 is 36, 7 times 7 is 49, 8 times 8 is 64, 9 times 9 is 81, 10 times 10 is 100. Next would be 121, 144, 169, and then so on. But I'm just multiplying a number by itself to get the perfect square. So again, everything in this list is called a perfect square. Now, if you don't find a number in this list, it will not be called a perfect square. It will be called an imperfect square. Okay? They are numbers not in the list above. So I can name something that's not in the list above. 31 is not in the list above, so 31 is an imperfect square. 132 is not in the list above, so it's not a perfect square. 3 is not in the list above, so it's what we call an imperfect square. So anything that's not in that list of perfect squares is called an imperfect square. If it's not one, it's the other. Now let's talk about taking the square roots of perfect squares and imperfect squares before I go into integers, rational numbers, and irrational numbers. So 81 is in the list. It's a perfect square. You can take the square root of 81. The square root of 81, it just means what number times itself what gave you that 81. Well, that would be a 9. And if you're in upper level math or you had, 8th grade or above, then you would know actually the square root of 9 is plus or minus 9. But we're just going to look at what we call the principal square root, which is the positive part of it. 144 is in the list. The square root of 144, well, what number times itself gives you 144, and that is 12. 3 is not in the perfect square list, so 3 is an imperfect square. If you take the square root of 3, and let me just flip this over so you can see what I'm doing with the calculator. You think of what number times itself will give you 3. So I'm going to take the square root of 3. 3 square root. Okay, it's 1.732050807757. And if this calculator held more digits, it would just keep going in some random fashion, guys. So the square root of 7 is not going to be a whole number like the square root of 81, the square root of 144. So if it's an imperfect square and you take the square root of it, you're going to get some long, crazy looking decimal. But if you take the square root of a perfect square, like for instance, the square root of 81 or the square root of 144, you're going to get some nice, neat number. Okay? And it works the same if you had a negative. Suppose you had the opposite or negative square root of 36, then you would end up with negative 6 for the answer. You just bring this down. Square root of 36 is 6. Now, don't get that confused with something like this, because now the negative is underneath the square root symbol. That's an imaginary number. We're not going to get into that. But if your negative's on the outside, you can simply bring it down, and square root of 36 is 6, if you have something like that. But again, If you take the square root of an imperfect square, you get some crazy looking decimal. Take the square root of some perfect square, you get a nice, neat whole number, okay? All right, so let's take a look at what integers are. Integers are simply whole numbers and their opposites. So when I say whole numbers, you start off with a number that looks like a whole, which is a 0. And then you just start counting by ones. So those are whole numbers, guys, and so forth. But it also says it includes the opposite. So opposites just means you change the sign. But 0 doesn't have an opposite. Okay, it's the only neutral number. It's neither positive nor negative. 1, however, has an opposite. It's -1. 2 has an opposite. It's -2. 3 has an opposite. It's -3. 4 has an opposite. It's -4. 5 has an opposite. It's -5, and so forth. Okay. So I can see that integers are just positive and negative whole numbers. That's it. And the number 0, the number that looks like a whole. For rational numbers, and guys, let me go back over something. If you have something that looks like this is a fraction, but 14 divided by 7 just equals 2. It's an integer as well because it's a whole number, okay? If you have something that looks like this equals -2. -2 is the opposite of this whole number, so it's an integer as well, okay? Basically, if you have a division bar and a divide and end up being a whole number or the opposite of a whole number, it's an integer as well. All right, rational numbers. Rational numbers is a simple thing. Instead of the long, drawn-out definition that the two, you have a fraction where A and B are written as a ratio and B cannot be 0. I'm not going to give that to you. The simple thing is for a rational number, it's any number that can be written as a fraction. Okay, think about some things you can write as a fraction. I can write -5 as a fraction. How? Because I can write this as -5/1. I can write 0 as a fraction. How? 0/1. I can write 2 as a fraction. How? 2/1. So all these integers are also rational, guys, because every one of those you can put over 1 and make it a fraction. So all integers are rational because they can all be made into fractions. Now you have things like 3 and 5/10. Well, 3 and 5/10 is a terminating decimal. It can be written as a fraction. It's 3 and 5/10. Just like you say it, you write it. Let me erase this so I have more room. Of course, the fraction itself, if you have 1/2, it's automatically a fraction, so it's automatically rational. But a lot of students get tripped over something that looks like this. The bar notation means it repeats, but you can also see it written like this with the ellipses indicating that the 4 and the 5 keep repeating. All repeating decimals are rational because they too can be written as fractions. So the type of rational numbers that we see, integers, all integers are rational because they can all be put over 1 and made into a fraction. All terminating, and when I say terminating, I mean it stops like 3 and 5/10. It stops somewhere in a place value. All terminating and repeating decimals are also rational. But we're going to look at one more thing, okay? All right, it says, I just forgot I had this down here, guys, so we're not going to worry about that. It says, how can an integer be written as a fraction? I told you all that. Just put it over 1. So all integers are rational. It says, how can a decimal such as 2 and 5/10 be written as a fraction? Well, you write it the way you read it, 2 and 5/10. This is read as 6,500, so you can write it as 65 over 100. This is read as 1 and 234,000, so you write 1 and 234 thousandths. These are all terminating decimals, guys, because they stop in some place value. All right, but remember, repeating decimals are also rational. Terminating and repeating decimals are rational. All right, now, let me show you one other thing. If you have something that looks like this, what is the square root of 25? Well, what number times itself gives you 25? That would be 5. 5 is an integer. All integers can be placed over 1. So therefore, the square root of 25 is also rational. Okay? All right, now let's go to something that's not rational. If it's not rational, it's irrational. It can't be both. The irrational numbers are the numbers whose decimal form neither repeats, I'm just going to put repeats nor terminates. So, for instance, if you have a decimal that looks like this, okay, and it just keeps going on. So I'll look at this. It's not repeating any particular pattern, and it's not terminating. I see that by the ellipsis. It keeps going on and on and on. So this is what we call irrational. Now, please don't assume that just because it doesn't terminate, it's irrational. Look up here at this one. This one right here. It had the little ellipsis too. But so that means it doesn't terminate. But the thing that made it rational is that it repeated. So if it repeats, it's automatically rational, guys. The thing that made this one not rational is that it didn't repeat, nor did it terminate. It's got to be both. Okay? Now, what about something like the square root of 3? So when I put that in the calculator and showed it to you in the beginning, when we were dealing with perfect squares and imperfect squares up at the top, we ended up with some crazy decimal. So I'm going to pull it back up. Let's get back to it. We ended up with 1.732050807757. Now, what did I say about that? That if the calculator held more digits, it just would have kept on going, okay? So we had 1.7320, blah, 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 blah. Okay, kept on going. This is some crazy looking decimal that it doesn't repeat, nor does it terminate, okay? This is also what we call irrational. So I'm going to tell you something, guys. Anytime you take the square root of an imperfect square, something that wasn't in that list at the top, you're going to end up with not a rational number, but an irrational number. But don't get it mixed up with the square root of a perfect square. Because earlier I gave you the square root of 25. 25 is a perfect square. It's just 5. If you take the square root of a perfect square, you get a rational number. If you take the square root of an imperfect square, you get an irrational number, okay? Don't get those two mixed up. All right, now let's talk about let me go give you something like this. You all know this. Pi Pi is just this long decimal approximation for the circumference of a circle divided by the diameter of that particular circle. And we normally approximate it at 3.14. But let me show you, that's just the approximation. Let me show you what it is for real. So I'm going to pull this up through Google. Pi decimal form. Okay. Okay, Kevin doesn't want to let me in that one. Okay, let me go back. Maybe I can get here. This is pi to 1,000 decimal places. Okay, that's pi to 1,000 decimal places. But that's just because somebody chose to stop at 1,000 decimal places out. But this number just really keeps on going. Okay, it's just very long and it's crazy. So pi, let me go back here. Pi is definitely irrational. Okay, this is just, don't get it confused. This is just an approximation because pi is an irrational number. It keeps on going. So although that's the approximation, pi is actually irrational because it keeps on what? Keeps on going. This is only an approximation. All right, now let's talk about real numbers, guys. So real numbers, I'm just going to put any number, okay? Or all numbers, basically. Unless they're imaginary, and we're not going to discuss imaginary right now. All right, so let's take a look at something that's going to be on your ACT prep practice that you're about to take. So before you get into those practice problems, I wanted to go over this. If we multiply an integer by another integer, will we get a rational or irrational number? So what you do is you just make up an integer. So I got the integer 5. I multiply by another integer. So I may multiply by the integer 4. Well, I get 20. 20 is an integer. Even if you had, and it's rational, guys, an integer is rational. Suppose you took the integer -3 and you multiply it by the integer 7. Well, you get -21. That's also rational. It's safe to say that if you take an integer and multiply by another integer, you're going to end up with a rational number. What about if we divide a rational number by an irrational number? So if I take something like 25 and I divide it by an irrational number like the square root of 3, what will I get? I'm going to take my handy dandy calculator. Let's just see what we'll get. Let's clear this out. And I'm going to do 25 divided by the square root of 3 and see what that equals. Well, we get some crazy looking decimal. So it's pretty safe to say 0.63, blah, 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 blah. I don't know what it was. All right, so I know it was crazy. That's irrational. And if you check it again, guys, you're going to get something that's also crazy looking. Okay? If you take a rational number and multiply by an irrational number too, like maybe let me do another, like 2 times pi. Well, 2 times pi is just 2 pi. You end up with, I'll do that on the calculator. But don't hit the approximation if you're going to use the calculator. And guys, on the ACT, you can use the calculator. I would suggest you just get a scientific one. So let's do 2 times, and don't hit 3.14, the approximation. Actually hit pi, and then hit enter and see. We get some crazy looking decimal again. 2 was rational and pi was irrational. So we still end up with some irrational number, okay? Again, multiplying a rational by an irrational is going to be irrational. What if we multiply an irrational number by another irrational number? Will we get a rational one or an irrational result? So let's take an irrational number like the square root of 3 and multiply by the square root of 5. Well, both of those are imperfect squares, so they're both irrational. I end up with the square root of 15. 15 is not on the perfect square list, so this is irrational. All right, what if I do the square root of 2? 2 is not on the perfect square list, times the square root of 8. 8 is not on the perfect square list. So both of those are irrational. The square root of 2 times the square root of 8 is the square root of 16. But the square root of 16 is rational because 16 is a perfect square. The square root of 16 is 4, so I get a rational number. So it says, will the result be rational or irrational? And I'm going to put it can be either. In other words, it can be both, guys. This is also on the ACT practice that you're about to take. Consecutive integers. Consecutive integers are just numbers that are one after another. They count up by ones. And I'll just give you some examples. Like 2, 3, 4, 5, 6. Those are consecutive, okay? Because they're one after another. Or 105, 106, 107, 108. Those are consecutive. They count up by one. Consecutive odd integers count up by 2. So you might have something like, and it has to be an odd number to start out with. 5 is odd. Just count up by 2. 5, 7, 9, 11, 13, and so forth. Or you might have something like 81, 83, 85. They count up by 2. 87, blah, blah, blah. Consecutive even. They also count up by 2. But you just got to start off with an even number like 4. Go up by 2, you get to a 6. Go up by 2, you get to an 8. These are consecutive even. 106, 106, 108. Just make sure you're counting up by 2. Those are consecutive even. So before you do the practice, you'll need to be familiar with those are. And let me just double check to make sure I cover everything that's on that practice. I hope you're going to be okay with positive and negatives multiplying. You can have consecutive odd and even integers that are negative. So for instance, if you had something like started off with consecutive odd, negative 11. If you go up by 2, it puts you at negative 9. If you go up by 2, it puts you at negative 7. Up by 2, it puts you at negative 5, and so forth. Works the same for even. If you have something like negative 24, if you go up by 2, it puts you at negative 22. Up by 2, it puts you at negative 20. Up by 2, it puts you at negative 18. Okay, so you can have positive and negative consecutive, even and odd integers. All right, but that's it. You should be able to do the practice that you're going to have to look at after this video, okay? Or actually do after this video. It's 8 problems. All right, that's it, guys. Thanks.